Beneath the rolling green hills and quiet villages of the Swiss countryside lies one of the most sophisticated and powerful scientific instruments ever created by humankind, the Large Hadron Collider, LHC. This sprawling underground facility, stretching across the border between Switzerland and France, represents humanity's most ambitious effort to unlock the secrets of the universe. Built and operated by CERN, the European Organization for Nuclear Research, the LHC is a technological marvel, designed to probe the deepest layers of physical reality. For over a decade, the LHC has been pushing the boundaries of scientific understanding by accelerating subatomic particles to near-light speeds and smashing them together in high-energy collisions. It has given scientists glimpses into the conditions that existed just moments after the Big Bang. In 2012, the LHC made headlines worldwide when it confirmed the existence of the Higgs boson, also known as the God particle, a discovery that earned a Nobel Prize and completed the standard model of particle physics. But now, something unexpected has emerged. Recent experiments conducted deep within the collider's tunnels have revealed anomalies so profound and puzzling that they are challenging the very foundations of modern physics. These strange phenomena have sparked a storm of speculation and concern among leading physicists, with some whispering that CERN may have uncovered something far more powerful and potentially dangerous than they ever intended. Rumors of inexplicable data patterns, unusual energy signatures, and even the possible detection of particles that don't belong in our known universe have started to circulate. As researchers scramble to verify the results, one question is becoming increasingly urgent. What has the Large Hadron Collider really discovered? And are we ready for the truth? Why are scientists like Michio Kaku alarmed by CERN's latest experiments? In recent months, whispers of extraordinary discoveries and unsettling possibilities have echoed through the corridors of the global scientific community. Among those raising eyebrows is none other than Dr. Michio Kaku, the world-renowned theoretical physicist and futurist. Known for his ability to translate complex scientific ideas into understandable insights for the public, Dr. Kaku has never shied away from bold questions about the future of humanity, but even he now appears visibly concerned about the latest developments at CERN. So, what exactly is happening beneath the Alps? What revelations have emerged from the Large Hadron Collider that could possibly prompt speculation about doomsday scenarios? The stakes are nothing short of astronomical. The LHC, often called the atom smasher, has always straddled the line between brilliance and danger. Capable of accelerating particles to 99.999999% the speed of light and smashing them together with energies never before produced on Earth, the collider mimics conditions not seen since the birth of the universe itself. These monumental collisions have allowed scientists to peer into the subatomic world, discovering particles, forces, and phenomena previously confined to theory. Before its launch, some experts and skeptics worried aloud, what if we accidentally created a black hole? What if we opened a portal to another dimension? Could we unleash energies that Earth was never meant to experience? Those concerns were largely dismissed as science fiction, until now. New data emerging from LHC experiments suggests the detection of highly anomalous energy patterns, behaviors that defy the current laws of particle physics. These readings have baffled scientists and prompted intense scrutiny. While CERN maintains a tone of calm curiosity, others, including Michio Kaku, are calling for caution. According to Kaku, we are possibly stepping into a new chapter of physics, one that may unravel not just scientific understanding, but even the fabric of reality as we know it. Is it simply an incredible leap forward for science? Or have we crossed a threshold into something we cannot fully control? As speculation mounts and public concern grows, many are asking, should the LHC be shut down? Are we toying with forces beyond comprehension? The truth, as we'll uncover in the next part of this story, is as fascinating as it is unsettling. The return of the LHC and a disturbing new chapter. For decades, humanity's understanding of the universe teetered on the edge of the unknown. The very laws that govern our existence, gravity, quantum mechanics, time and space, formed only a partial portrait of a vast and intricate cosmic tapestry. Many of the most profound mysteries, such as the nature of dark matter, the origins of mass, and the fundamental structure of reality, remained cloaked behind an impenetrable veil. And scientists could theorize and speculate, but they lacked the tools to test these ideas in the crucible of real-world data. That all changed with the birth of the Large Hadron Collider, LHC-PHA machine, so powerful, so precise, that it could recreate conditions just moments after the Big Bang. Situated deep beneath the peaceful Swiss-French border at CERN, the European Organization for Nuclear Research, the LHC became more than just a scientific instrument. It became a doorway. One capable of peering into realms of existence we once thought were forever hidden. The Collider made history in 2012 with the discovery of the Higgs boson, a particle long theorized but never before observed. This breakthrough not only earned a Nobel Prize, but also validated the standard model of particle physics, the framework used to understand how the universe behaves at its most fundamental level. But for all its triumphs, the LHC went quiet into 2019, entering a planned 3-year hiatus for upgrades. Then, in April 2022, the machine roared back to life. This marked the beginning of Run 3, a new era of high-energy experimentation that would continue until 2024. With enhanced detectors, increased beam energy, and upgraded computational capabilities, the LHC was now more powerful than ever before. Scientists around the world eagerly anticipated a flood of new discoveries, many of which were expected to challenge the boundaries of known physics. But amidst the excitement, a chilling announcement from CERN began to circulate. In a statement that surprised even seasoned researchers, CERN hinted at unexpected results that do not align with established models. Though vague in language, the tone of the communication sparked immediate speculation. Had the LHC found evidence of a new force of nature, or something even more exotic, such as extra dimensions, unknown particles, or destabilizing phenomena? Whispers of abnormalities in particle decay rates, anomalies in high-energy collisions, and energy distributions that seemingly violated conservation laws started to spread. What once felt like a methodical, controlled exploration of subatomic particles had suddenly become a foray into uncharted territory. Renowned physicists like Dr. Michio Kaku began to speak out, not out of fear-mongering, but concern. In his view, humanity may be on the verge of breaking through the ceiling of known physics, stepping into a domain where our current understanding no longer applies, and where the consequences could be unpredictable. As the scientific community holds its breath, CERN's vague statement continues to ripple across media channels and theoretical forums alike. What could be so profound and so potentially dangerous that even the world's most confident researchers are beginning to question the course of these experiments? In the next chapter of this story, we'll dive deeper into the possibilities, from miniature black holes to parallel universes and the deeply unsettling idea that reality itself may not be as stable as we once believed. The heart of human curiosity. Activating the Large Hadron Collider. In one of the most ambitious scientific endeavors in human history, the Large Hadron Collider, LHC, was brought to life through a monumental collaboration involving over 10,000 scientists and hundreds of universities and laboratories spread across the globe. This international partnership, led by the European Organization for Nuclear Research, CASRRN, set out to construct a machine that could answer the most profound questions ever asked about our universe. Between 1998 and 2008, the LHC took shape, an engineering masterpiece hidden deep beneath the tranquil countryside near Geneva, straddling the border between France and Switzerland. At the core of this marvel is a 27-kilometer, 17-mile circular tunnel, buried approximately 175 meters underground, where conditions rival the earliest moments of the universe itself. In 2010, history was made. The LHC achieved its first particle collision at an energy level of 3.5 tera-electron volts per beam, nearly 4 times greater than any previous collider on Earth. The record-breaking event marked a turning point in particle physics. It was a bold step into the unknown, and the world held its breath. But CERN didn't stop there. Through a series of advanced upgrades and enhancements, the collider's power grew exponentially. Today, the LHC can accelerate particles to an astonishing 6.5 TeV per beam, enabling experiments that were once thought to be the stuff of science fiction. At the core of the LHC's scientific capabilities lie 4 primary collision points, precise locations within the ring where 2 beams of particles are made to collide head-on at nearly the speed of light. Around these collision points are stationed 7 sophisticated detectors, each meticulously designed to observe and analyze specific types of particle interactions. Each detector tells a different part of the story. From Atlas, the largest detector tasked with studying everything from dark matter to extra dimensions, to CMS, which helped confirm the existence of the Higgs boson. These instruments act as the eyes and ears of the collider, capturing fleeting subatomic phenomena that exist for just fractions of a second. Together, these detectors and collision points form the neural network of the LHC, enabling us to delve deeper into the very fabric of reality. But as the collider's power continues to increase, so do the stakes. Every collision has the potential to uncover phenomena that challenge the fundamental assumptions of physics. With the LHC now entering its most ambitious phase yet, scientists are beginning to observe strange anomalies and unexplained behaviors, sparking both excitement and caution among the world's leading physicists. What lies ahead? What forces, particles, or even dimensions might the LHC unlock next? Stay with us as we continue exploring the enigmatic breakthroughs, unanswered questions, and possible dangers that are now emerging from the world's most powerful machine, beyond protons, unlocking deeper secrets with the LHC. While the Large Hadron Collider, LHC, is primarily renowned for its proton-proton collisions, its capabilities extend far beyond smashing just those subatomic particles. In a feat of engineering versatility, the LHC is also equipped to accelerate heavy ion beams, such as those composed of lead nuclei, opening new avenues of exploring the most extreme states of matter in the universe. Each year, CERN dedicates approximately 1 month to conducting heavy ion collisions, allowing scientists to recreate conditions similar to those just microseconds after the Big Bang. During the rest of the year, the focus returns to high-energy proton-proton experiments, which continue to be the cornerstone of the Collider's mission. At its core, the fundamental goal of the LHC is to test and validate the predictions of particle physics theories, particularly those described by the Standard Model, a theoretical framework that outlines the fundamental particles and the forces that govern their behavior. The LHC is also a key instrument in investigating new physics beyond the Standard Model, such as the elusive world of supersymmetry, which proposes the existence of an entire hidden realm of partner. A major highlight in the LHC's journey came in 2012, when it famously confirmed the existence of the Higgs boson, the long-sought particle that gives mass to everything in the universe. Since then, physicists have used the collider to probe the Higgs boson's properties, hoping to uncover signs of deeper layers of reality still hidden beneath the surface. But what exactly is a hadron, and why does it matter? The term hadron refers to composite subatomic particles made up of smaller constituents called quarks, which are held tightly together by the strong nuclear force, the most powerful of the 4 known fundamental forces in nature. This force is analogous to how electromagnetism binds atoms into molecules, but on a much smaller and more powerful scale. There are 2 main types of hadrons: baryons, such as protons and neutrons, which make up the nuclei of atoms; mesons, like the pion and kaon, which are often produced in high-energy interactions, and were first discovered in cosmic ray experiments during the late 1940s and early 1950s. To study hadrons and their interactions, physicists need extremely high-energy environments, far beyond what can be achieved naturally on Earth. That's where colliders come into play. A collider is a highly specialized type of particle accelerator that pushes beams of particles in opposite directions at nearly the speed of light, eventually slamming them into each other to create tiny fireballs of raw energy. These collisions produce a flurry of particles, often for mere billionths of a second, allowing scientists to observe processes that haven't occurred naturally since the dawn of the universe. Though building and operating these massive machines is immensely challenging and expensive, their scientific payoff is priceless. Unlike fixed target experiments, where particles are fired at stationary material, colliders can achieve much higher center of mass energies, vastly increasing the probability of generating rare or never-before-seen particles. In essence, colliders like the LHC function as cosmic microscopes, peering into the very building blocks of existence, recreating conditions from the early universe and enabling breakthroughs that redefine our understanding of the cosmos. Peering into the quantum abyss, the anatomy and design of the LHC. What makes the Large Hadron Collider such a powerful window into the fabric of the universe isn't just its immense energy, but its ability to produce rare and fleeting subatomic byproducts, particles so short-lived that they exist for less than a fraction of a second before vanishing. These byproducts, created in high-energy collisions, are the only clues scientists have to explore realms that otherwise remain inaccessible. Many of these particles do not occur naturally on Earth anymore. They can only be reproduced in extremely energetic environments, just like those that existed in the moments following the Big Bang. By studying these ultra-short-lived particles, physicists can test theoretical models, understand how forces interact at the quantum level, and possibly reveal entirely new physics that extend beyond the boundaries of our current knowledge. But achieving this level of exploration requires extraordinary engineering, beginning with the colossal underground tunnel that houses the LHC's tunnel, which spans a circumference of 27 kilometers, 17 miles, is buried at varying depths of 50 to 175 meters, 164 to 574 feet, beneath the Earth's surface. This depth variation wasn't random. It was a meticulously planned engineering decision. The reason? To minimize tunneling beneath the Jura Mountains, which lie to the northwest of the collider. Avoiding these mountains eliminated the need for constructing vertical access shafts, which would have added massive cost and complexity. Instead, scientists and engineers cleverly routed the tunnel through the natural lowlands, reducing excavation costs while minimizing environmental and structural disruption. Additionally, the Earth itself plays a vital role in shielding the collider from unwanted cosmic interference. The crust acts as a natural radiation barrier, protecting the sensitive detectors inside the collider from cosmic rays and background noise that could otherwise distort experimental data. The tunnel was originally constructed between 1983 and 1988 for CERN's earlier collider, the Large Electron Positron Collider, LEP. Later, it was repurposed and expanded for the LHC. Within this ring, 3 parallel concrete-lined tunnels, each 8 meters wide, form the backbone of one of humanity's most ambitious scientific projects. These underground corridors are not just silent passageways of science, they are cathedrals of inquiry, where beams of particles travel at 99.99999% the speed of light, guided by powerful superconducting magnets chilled to temperatures colder than outer space. Every decision in constructing this subterranean marvel was informed by both precision physics and practical constraints. The result is not just a scientific instrument, it's a statement of what humanity can achieve when curiosity is matched with cooperation and ingenuity. The Large Hadron Collider itself traces the border between Switzerland and France at 4 specific points, but the majority of its vast 27-kilometer tunnel lies beneath French soil. Above ground, the surface-level facilities serve as vital hubs, housing critical support systems such as compressors, ventilation units, control electronics, and refrigeration plants, essential for maintaining the ultra-cold temperatures needed by the collider's superconducting magnets. The staggering amount of data produced by the LHC is mind-boggling. Each year, it generates approximately 15 petabytes of data. That's equivalent to thousands of times the entire contents of the Library of Congress. To manage this torrent of information, CERN developed an extensive computing grid network, a vast interconnected system of thousands of computers distributed worldwide. This network allows scientists from hundreds of institutions across the globe to access, analyze, and simulate the data generated from particle collisions. Building the LHC was an immense financial and engineering undertaking. The total cost soared to nearly 7.5 billion euros, making it one of the most expensive scientific instruments ever built. Initially approved in 1995 with a budget of 2.6 billion euros, and an extra 210 million euros dedicated to its experimental apparatus, the project faced significant challenges before finally becoming operational. On September 10, 2008, the LHC was officially launched, but shortly after, an unforeseen setback struck. A magnet quench incident. A sudden loss of superconductivity in the magnets caused severe damage to over 50 superconducting magnets, their mountings, and the vacuum pipes. This mishap forced a 14-month delay while repairs were undertaken, extending the long wait for the collider's full operation. Despite this early hurdle, the LHC's first successful run from 2010 to 2013 revolutionized physics. It achieved proton collisions at energies up to 4 tera-electronvolts, TeV per beam, and also collided lead nuclei, opening new windows into the quantum world. Among its landmark discoveries was the detection of the Higgs boson, the particle responsible for giving mass to other fundamental particles, a finding that earned the 2013 Nobel Prize in Physics. The LHC also identified exotic composite particles like the bottomonium state and produced fleeting states of quark-gluon plasma, the primordial form of matter thought to have existed just moments after the Big Bang. These breakthroughs marked the LHC as a powerful engine for discovery, forever changing our understanding of the universe's smallest and most mysterious components. Ultimately, the Large Hadron Collider achieved one of its primary scientific goals: to explore and confirm the existence of the elusive Higgs boson. This particle is a cornerstone of the Standard Model of particle physics, a theoretical framework describing the fundamental forces and particles that compose our universe. For decades, the Higgs boson remained purely theoretical. Its substantial mass and complex nature made it nearly impossible to detect with earlier technologies. CERN scientists predicted that if the Standard Model was accurate, the LHC would produce multiple Higgs bosons every minute during high-energy collisions. This capability enabled physicists to finally verify the particle's existence with undeniable evidence, transforming theory into confirmed reality. Beyond the Higgs, the collider has also been instrumental in probing the existence of supersymmetric particles, another speculative phenomena that could extend or even revolutionize our understanding of particle physics. Following its initial 3-year operational run from 2010 to 2013, the LHC underwent a lengthy pause for vital upgrades. The collider resumed operations in 2015, entering its second phase, which continued until 2018. After another scheduled shutdown, it was once again reactivated in April 2022 with enhanced capabilities, including a maximum beam energy upgraded to 6.8 tera-electronvolts, the AV. This third run is expected to last until 2026. Promising even more profound insights into the subatomic world. Yet, amidst the excitement of this third run, a mysterious and perplexing event shook the scientific community. An unexpected anomaly that has left researchers searching for answers and ignited concerns among even the most renowned physicists. On July 7, an unusual and mysterious crack appeared within Earth's magnetic field. Unlike a fleeting lightning flash, this peculiar tear persisted for an astonishing 14 hours. This prolonged opening acted like a gateway, allowing powerful solar winds to pour through and trigger intense geomagnetic storms. These storms, in turn, unleashed spectacular and mesmerizing auroras. Dancing lights that lit up the skies with breathtaking colors and patterns. Scientists watching the auroras were so captivated by their beauty that many found it nearly impossible to look away. Yet, amid this natural wonder, a pressing question lingered. What caused this sudden crack, and how could it possibly be connected to the Large Hadron Collider? The answer lies in a rare solar phenomenon called a co-rotating interaction region, or CIR. CIRs are enormous plasma structures formed within the Sun's heliosphere, the vast bubble carved out by the Sun's magnetic field and the solar wind. They develop where fast-moving solar wind streams collide and interact with slower ones, creating complex and turbulent regions of energized particles. Much like coronal mass ejections, CMEs, which are explosive bursts of solar material, CIRs are propelled outward from the Sun, traveling through the solar system. However, CIRs differ in their formation and behavior, often lasting longer and having distinct impacts on planetary magnetic fields, including Earth's. As the so-rotating interaction region, or CIR, traveled toward Earth, it carried with it powerful shock waves and compressed magnetic fields. These energetic disturbances spark tumultuous space weather phenomena that often manifest as stunning auroras, ethereal light shows that dance across the polar skies. In the early hours of July 7th, this particular CIR made direct contact with Earth's magnetic field, setting off a sustained G1 class geomagnetic storm. A mild but noteworthy event in space weather terms, according to assessments from the National Oceanic and Atmospheric Administration, NOAA. Analysts also detected a coronal mass ejection, CME, embedded within the solar wind that preceded the CIR, adding further energy and complexity to the solar storm that struck our planet. With the dramatic nature of the magnetic crack and the resulting geomagnetic storm, a vital question naturally arises: should the public be alarmed? Experts are quick to reassure that there is no cause for panic. Fissures in Earth's magnetic field are relatively common occurrences, natural fluctuations in the invisible shield that protects our planet from the harsh effects of solar storms. This magnetic shield, generated by Earth's molten core, serves as a crucial barrier, deflecting charged particles emitted by the Sun and preventing them from wreaking havoc on our atmosphere, satellites and power grids. While many such cracks or openings in the magnetic field tend to open and close quickly, sometimes lasting only minutes or seconds, recent observations reveal that these fissures can sometimes remain open for extended periods, spanning several hours. These prolonged openings allow more solar particles to enter the near-Earth environment, increasing the intensity and duration of geomagnetic storms. However, despite the spectacular auroras and the sustained magnetic crack witnessed on July 7th, scientists emphasize that these events are part of the dynamic nature of Earth's magnetosphere. The magnetic field is not static. It constantly fluctuates and adjusts in response to solar activity, maintaining a delicate balance that has shielded life on our planet for billions of years. Back in 2003, Harold Freyer, the lead author of a pivotal study on this very phenomenon, offered a vivid analogy to help us understand Earth's magnetic shield. He compared it to a drafty house during a storm, with a window left wide open. This image perfectly illustrates how, despite the magnetic shield's primary role of deflecting solar storms, some energy can still slip through the gaps, much like how a storm blowing through an open window might damage a couch inside the house. In the same way, Earth's magnetic shield typically protects us from space weather, but occasionally energy sneaks through its fissures. These breaches can sometimes cause disruptions, such as failures in satellite operations, radio communications, and even power grids. Fortunately, the magnetic crack that appeared on July 7th did not trigger any such technological failures. Instead, it gifted residents across Canada and parts of the United States with breathtaking displays of the Northern Lights, highlighting the awe-inspiring and beautiful effects of this celestial breach. Adding another layer of significance, scientists have revealed that the Sun is approaching the most active phase of its 11-year solar cycle, a phase that is arriving earlier than previously predicted. This heightened solar activity means we can expect an increased frequency of spectacular auroras over the next 3 years, offering even more opportunities to witness the natural wonders born from the Sun-Earth connection. Meanwhile, the Large Hadron Collider's recent achievements extend far beyond detecting this magnetic field crack. In 2017, the public was introduced to numerous analyses based on the vast data sets collected during 2016. That year marked an intensive period of research into the properties of the Higgs boson, the particle that plays a critical role in our understanding of how fundamental particles acquire mass. Alongside improvements in the precision of experimental results, the Large Hadron Collider has continued to push the boundaries of particle physics. From March 2021 onward, the LHC experiments revealed the discovery of 59 new hadrons, based on data gathered during the Collider's first 2 operational phases. These discoveries mark a remarkable milestone in our understanding of the subatomic world. A particularly significant breakthrough came on July 2nd, 2022, when researchers announced the observation of a previously unknown variety of pentaquark, an exotic particle consisting of 5 quarks. This newly identified pentaquark is composed of a charm quark, a charm antiquark, an up quark, a down quark, and a strange quark. This discovery emerged from detailed studies of charged B meson decays, shedding new light on the complex interactions governing quark behavior. However, as is typical in particle physics, the initial rush of groundbreaking results gradually slows down over time. With each passing year, the number of new discoveries diminishes as the most obvious findings are uncovered. To combat this natural decline in discovery rate, scientists have planned significant upgrades to the collider itself. These upgrades aim to increase the collider's collision energy, luminosity, the number of collisions per second, and detector sensitivity. One ambitious plan under consideration is to raise the collision energy to a staggering 14 tera-electron volts LeV, nearly doubling the current levels. This enhanced version of the collider, known as the High Luminosity Large Hadron Collider, HLEHC, began its upgrade process in June 2018. The primary goal of the HLLHC is to boost the machine's luminosity, substantially increasing the chances of detecting extremely rare particle interactions and refining the precision of measurements. By enabling more intense and frequent particle collisions, the HLLHC will open new frontiers for exploring the fundamental building blocks of matter and the forces that govern the universe. Statistically marginal measurements characterize some of the findings in the ongoing 3rd run of the Large Hadron Collider, which serves as an intermediate phase within the collider's broader research program. Each run has progressively deepened our understanding of particle physics. Run 1 was defined by the historic discovery of the long-anticipated Higgs boson, a breakthrough that revolutionized the field. Following this, Run 2 unveiled several significant decay modes of the Higgs boson, further validating its pivotal role as the source of mass for fundamental particles. But what exactly is the Higgs boson, and why does it hold such immense significance in our understanding of the universe? To answer this, we must journey back to the very origins of the cosmos, a time immediately following the Big Bang. The early universe was an extraordinarily hot, dense, and rapidly expanding environment, a chaotic blend of particles, energy, and radiation. As the universe expanded and cooled, a profound transformation took place, the activation of the mysterious Higgs field. The Higgs field is an invisible energy field permeating all of space. As particles move through this field, they acquire mass, a fundamental property that allows matter to clump together, form atoms, stars, planets, and ultimately life itself. Without this interaction, particles would remain massless, zipping through space at the speed of light, and the universe as we know it, with its galaxies and complex structures, would never have come into existence. In this grand cosmic framework, the Higgs boson emerges as a key player, a particle inherently linked to the Higgs field. It can be thought of as a tangible manifestation or excitation of this field, a proof of its existence and function. Scientists often describe the Higgs boson as the universe's answer to the missing piece in our understanding of how particles gain mass, much like the solution to a complex puzzle that unlocks a deeper comprehension of reality. The predicament of conferring essential mass upon all other particles lies at the very heart of the Higgs boson's significance. Yet, its importance extends far beyond simply being a foundational component of the universe. Without the Higgs field, fundamental particles would perpetually travel at the speed of light, making the formation of atoms, molecules, and all the intricate chemistry and biology that underpin life utterly impossible. The very fabric of reality would be profoundly different, rendering our existence as conscious observers inconceivable. In the absence of the Higgs field, fundamental particles would be trapped in an eternal sprint, racing relentlessly at light speed, forever unable to slow down, stop, or combine to create the matter that forms everything we know. This relentless motion would preclude the complex interactions necessary for the universe as we experience it. The discovery of the Higgs boson marked a monumental milestone in particle physics, confirming a critical piece of the Standard Model. This achievement was so transformative that it earned Peter Higgs and François Englert the Nobel Prize in Physics in 2013, recognizing their theoretical prediction made decades earlier. However, the story does not end there. Even as the Higgs boson helped illuminate one of nature's great mysteries, the cosmos continues to harbor profound secrets. Within the known universe, 4 fundamental forces govern the behavior of matter and energy: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Yet tantalizing whispers from the farthest reaches of space suggest the existence of a 5th force, hidden and elusive, waiting for discovery. This mysterious force could potentially reshape our understanding of physics and unlock new realms of cosmic phenomena. Speculation has long linked this mysterious 5th force to the enigmatic substance known as dark matter, an untouchable form of matter that makes up roughly 27% of the universe's total content. Some theorists even suggest that this elusive 5th force could be deeply connected to the existence of extra dimensions, hidden layers of reality beyond our everyday perception. But where can we find the key to unlock these cosmic mysteries? The answer, many believe, lies within the Higgs boson itself, a beacon of hope, much like a guiding light at the end of a dark tunnel, illuminating the path toward new understanding. As the scientific quest for answers intensifies, so too have the concerns voiced by those wary of what meddling with such fundamental forces might unleash. The Large Hadron Collider, the powerful instrument designed to probe the universe's deepest secrets, has become entangled with fears about catastrophic consequences, even extinction. Some imagine the LHC as a hidden gateway to otherworldly realms, capable of opening portals that could release demons or nightmarish creatures into our reality. Others speculate wildly that the collider conceals a devastating weapon, one that could obliterate the planet with a simple flick of a switch. And there are those who entertain even more conspiratorial notions that the LHC is part of an elaborate government scheme designed to manipulate minds, turning humanity into unthinking automatons. Others go even further, claiming that the Large Hadron Collider is engaged in deeply sinister pursuits. These theories suggest that the particle collisions inside the LHC are part of a covert governmental experiment aimed at shaping a new world order, one where only an elite few would survive. At the heart of this apocalyptic vision lies the concept of a false vacuum. A false vacuum is a theoretical state of space where the energy is not at its true lowest level, making it inherently unstable. If the LFC were to trigger a transition from our current vacuum state to a false vacuum, it could unleash a cascade of catastrophic events, potentially obliterating everything we hold dear. While this doomsday scenario might sound like science fiction, the possibility, though extremely remote, cannot be completely ruled out. Some experts argue that the extreme energies produced by the LHC could create conditions conducive to the formation of a false vacuum bubble, which might expand at the speed of light, annihilating the fabric of our universe. The fears don't stop there. The creation of microscopic black holes, capable of growing uncontrollably and swallowing entire galaxies, is another nightmare scenario tied to these experiments. The profound gravity of such risks has captivated imaginations, evoking comparisons to the infamous snap by Thanos in the Marvel Cinematic Universe, where half of all existence suddenly vanished. In reality, such a cosmic collapse, where the universe itself crumbles into nothingness, is a scenario of immense theoretical consequence, one that challenges and could ultimately revolutionize our understanding of reality itself. Although the possibility of creating black holes within the LHC is extremely unlikely, the potential consequences of triggering a false vacuum transition are so severe that they cannot be dismissed outright. But why hasn't such a catastrophic event occurred yet? The answer lies in the nature of the Higgs field, which plays a central role in the concept of a false vacuum. For the Higgs field to shift from its current false vacuum state to a lower energy, true vacuum state, it would have to overcome an enormous energy barrier through a process known as quantum tunneling. This barrier is so immense that the time required for such a transition to naturally occur is estimated to far exceed the age of the universe itself. In other words, while the theoretical possibility of a universe-ending collapse exists, it is not something that poses any immediate or practical threat. The Higgs field remains metastable, temporarily trapped in its current false vacuum state, allowing the universe to persist as we know it. Meanwhile, CERN continues its ambitious scientific journey. The Large Hadron Collider's third run, which began recently, is projected to continue until 2025, with the goal of doubling the current data collected. Following this, CERN plans an extended pause lasting until 2029 to upgrade the facility. When the LHC returns to full operation after this break, it will be capable of generating particle collisions at a rate 10 times greater than today, ushering in an era of unprecedented precision and discovery. This milestone will mark the beginning of the Large Hadron Collider's fourth run, anticipated to extend until 2042. By the time this phase concludes, the LHC is expected to amass a data set nearly 10 times larger than that projected at the end of the third run. Looking ahead, the fourth run promises to not only corroborate the theories and hypotheses that arise from the experiments and analyses of the third run, but also to expand our understanding even further. Each run of the LHC represents a deliberate and incremental progression within its overarching program. Every phase builds upon the achievements of its predecessor in an unbroken quest for scientific discovery. Peering into the future, the culmination of the LHC's efforts signals an even deeper exploration of the universe's most profound mysteries. The evolution of the LHC summarizes a story of gradual advancement, punctuated by tantalizing revelations. As it forges forward through its third run and beyond, each collision event contributes incrementally to our collective knowledge. This systematic expansion of understanding offers unprecedented access to the hidden complexities of the cosmos. The third run acts as a critical bridge, linking past experimental triumphs to the uncharted frontiers that await scientific investigation. Although this journey unfolds step by step, its potential to revolutionize our grasp of the universe's inner workings is immense. In this unfolding chronicle of the LHC program, the spirit of scientific inquiry shines brightest, methodically unraveling the cosmos's puzzles through each collision. As we delve ever deeper into the subatomic realm, we edge closer to revealing the universe's most profound secrets. Fueled by the dedication of brilliant minds and the extraordinary capabilities of the LHC, the third run stands as a pivotal chapter in this narrative, laying the groundwork for the insights, revelations, and paradigm-shifting breakthroughs that will define our scientific voyage for decades to come.